In the last video, we talked about angular momentum, and we said that there are two particular equations that we have for it. The angular momentum is I omega, and that torque times time is equal to the change in angular momentum. And remember that those pair with the linear equations. Now, there's one more thing that I want to add to it, and that is that not only can angular objects or objects that are rotating produce an angular momentum, but so can linear objects. And if you think through this, I still need to add my linear equivalent to convert angular to linear. And so what it's going to be is it's going to be r cross momentum, or r cross rho, or r cross p. And so that we have this equation now where this would be the angular momentum of rotating objects, and this would be the angular momentum for not rotating objects. Now, you might ask, when does that happen? I'm glad you asked. So we have a pulley system here that has a mass of 2 kilograms, a radius of 3. I'm going to hang a weight off of it that is 6 kilograms, and I'm going to cause that weight to fall 2 meters. Now, as soon as I do that, isn't this 6 kilogram object applying a force at a distance away from a pivot point? So because it's applying a radius, it has a certain momentum going this way. That momentum is perpendicular to the radius. That means that it has to have an angular momentum. So what we want to do in this problem then is we want to find out, well, what is the torque acting on the pulley system? What is the acceleration, the linear acceleration of something on the edge of the pulley, or we could say the acceleration of the weight as it's falling? What's the velocity that it has at the bottom? What's the angular momentum that it has at the bottom? So the first thing that we're going to talk about is finding this torque. Thinking back to when we talked about torque in this chapter, we have an equation that mirrors this in a way that we have the I alpha, which is the F equals ma of angular, but then we also have the linear conversion part to it that is R cross F, or R times F. So whichever, depending on the ones I'm given here, is the one I'm going to use. So because I know the radius, which is 3, I also know the force of this, which will be the weight, 6 times 9.8, then I can say that my torque is equal to 3 times 6 times 9.8. And the torque acting on that is going to be 164 Newton meters. Part B. Now in part B, I want to find out what the linear acceleration is. Well, because this equation has angular acceleration, then I could really bring down the rest of this. This could have been combined into one part where we just put these two equal, but it wasn't. So here we go. So I can say that 176.4 is equal to I alpha. Now, because this is a pulley, we're going to say that these guys are massless. So I'm going to put on here massless spokes. That means all of the weight is on the outside, and if that's the case, then our moment of inertia has to be equal to mr squared. So I can say that this is mr squared. To convert angular acceleration to linear acceleration, we have A equals R alpha, which means that alpha is equal to A over R. And I'm making that be big R because that's going to be the radius of my pulley. So this will be A over big R. Now I can cancel out an R, and I'm left with mr times A. Well, I know what m is. This is the mass, that is the moment of inertia mass. It is the big mass, which is the mass of the pulley itself. So this can be 2 times the radius of the pulley, which is 3, times A. And when we divide that all over into the 176.4, then we get a linear acceleration of 29.4 meters per second squared. Halfway done. Now comes the interesting part. When we're talking about velocity at the bottom, we're going to go into energy now. So we're going to say over here we have a certain amount of energy. This is going to be part C. It has potential energy at the top. And by the time it gets to the bottom, there's going to be translational kinetic energy. Remember, that's the linear kinetic energy due to the 6 kilogram mass falling. And then there's going to be rotational kinetic energy because the pulley is going to be spinning. So I can say that this is mgh is my potential energy, translational kinetic energy 1/2 mv squared, kinetic rotational energy 1/2 I omega squared. Now all of this is in terms of linear, so how about we convert this to be in terms of linear also? So 1/2, we already said that our angular momentum up here is mr squared. To convert our angular velocity, remember our v equals r omega, which means that I can say omega equals v over r and plug that in. So I'm going to have v squared over r squared. My r squareds will cancel out, and I'm left with 1/2 mv squared plus 1/2 mv squared equals mgh. Now, at first thought, you might think, oh, I can cancel all these masses out. But they are different masses. So this is the mass that's falling, because that's the one that has the potential energy, which I'm going to say is little m. This is the one that's moving in a straight line, which again is that 6 kilogram mass. So it's also going to be little m. But this is the object that's rotating, which is the pulley. So it's going to be our big M. And we're looking for velocity, which means aren't these going to have, this will fall at the same velocity that something on the edge will have. So these two V's are the same. I can pull out the 1/2, have my M plus M times V squared equals mgh. And now I know everything except for V, so I can plug in my numbers. This will be 6 times 9.8. The height was 2 meters that it's going to fall. Half of 2 plus, or how about 6 plus 2? 6 plus 2, and v squared. And then when I solve for the velocity, I get a velocity of 5.42 meters per second. Awesome. Now, part D. We want to talk about momentum. If we are looking for the angular momentum when this reaches the bottom, so I'm going to have angular momentum, the symbol for it's an L, at the bottom. It has to equal the angular momentum of the mass plus the angular momentum of the pulley. So the angular momentum of the mass, we can look back at this and say it's going to be, because it's moving in a linear direction, I'm going to use this part. So I'm going to say RP, and then the mass of the pulley, because it's spinning, I'm going to use this part and say it's plus I omega. Now again, I'm stuck with this where part of this is linear, part of this is angular. Is it okay if I keep it that way? It is if we know all of the values. The problem is we don't know what I is, and we don't know what omega is. But we can find I basing off of this equation, the mr squared. So I'm going to plug in my mr squared here. And if I do that, then I also want to make this be in terms of what we talked about over here, that it's the v over r. One of my r's will cancel out, and I'll have mrv. Now again, this will be the mass of the pulley, so it's big M. And let's look then at the mass that's falling. So we'll have r, and remember that momentum is mass times velocity. What is that r? It's the big R, so I can say big R. This is the mass falling, which is little m. And then isn't that velocity going to be the same as that velocity? So I can take and pull out an RV out of both of those and say R times V times M plus big M has to equal the angular momentum that we have at the bottom. And now I can plug in values. I know my radius is 3. I know my velocity is 5.42. I know that the mass falling is 6, the mass of the pulley is 2, and I can plug all of those numbers in to find out that the angular momentum at the bottom is 130.1 kilogram meters squared per second. Now, you might say, why did we have to say the angular momentum at the bottom? Because I thought angular momentum was conserved. Well, it is, but remember that it's only conserved if there's no torque acting on the system. And because we have the 6 kilogram torque acting on the pulley, pulling it, then the angular momentum is not conserved. It will be increasing angular momentum as that falls because that velocity is increasing.